All right, what we're going to do in this segment, we're going to derive the heat diffusion equation. And if you recall from the last segment, what we did is we came up with an equation that enabled us to calculate the heat flux within an object. But we said that in order to be able to evaluate the heat flux, we needed to know the temperature distribution inside of the object. And so that's where the heat diffusion equation comes in. It's an equation, it's a partial differential equation, and we'll derive that. That enables us to determine the temperature within an object. And sometimes people will shorten it and they'll call it the heat equation or the heat diffusion equation. So this is going to be kind of a long segment because we've got to go through derivation and come up with this equation. But it's the best way to keep it continuous, and so that's why it's going to be a little bit longer. Let me begin with an overview of where we're going with this. Okay, so there we go. Now, when we're looking at this, one of the main things that we're after, we want to know the temperature distribution within an object. And notice that I've put the temperature distribution as a function of the three spatial dimensions and time. We will be looking later in the course at transient analysis. That's where you have temperature within the object changing with time as well as with spatial location. And so we'll derive the heat diffusion equation in the most general sense. But in order to be able to calculate the temperature within an object, we need to know a number of different things. And one of the things is going to be the surface conditions on that object. And so we need to know either the temperatures and or heat transfer rates. So those are the boundary conditions on the surface. And so that's another piece of information that we need to know along with the heat diffusion equation. So what we're going to do now, we're going to begin with the derivation of the heat diffusion equation, and we'll start by looking at a little infinitesimal chunk of the object, and then we're going to apply conservation of energy to that, and then we'll derive the equation from there. So let's begin with our little chunk of object. Okay, so here we have an object, and remember our goal, we want to be able to come up with an equation that enables us to determine the temperature within that object as a function of time and space. And speaking of space, this is our coordinate system that we will be using. Okay, so now what we're going to do, we're going to zoom in on a little cube within this object, and we're going to expand it. And within that cube, I'm going to show the heat flux and energy generation and storage going on within that. So let me sketch that out now. Okay, so there we have our little cube, and what I've shown is heat flux coming into and leaving all of the surfaces in our little cube. I've also shown on the inside we can have storage, so energy storage is shown there, and we can also have energy generation, and so this object could be storing and generating energy, and we'll talk about how you can generate energy as we go on. But to write that out, the storage. And so our storage is going to be, it's essentially MC delta T per unit time. And so you'll notice dx, dy, dz, that is the differential volume of our little differential element here. Multiply that by the density. That gives us mass, and then we're taking mass times the specific heat capacity times the change in temperature with respect to time. And notice that I'm using the partial derivative of temperature. That's because temperature is a function of space as well as time. And then for energy generation, we're going to define Q dot. Q dot is going to be the rate of energy generation within our solid, and then that's going to be watts per meter cubed, and then we need to multiply that by volume dx dy dz. So what we're now going to do, we're going to take all of this and we're going to apply the conservation of energy equation, the first law of thermodynamics, to this system, and that's going to give us an equation that we're then going to work with. Okay, so with the first law, what we can say is the energy flowing in plus the energy being generated minus energy leaving is equal to energy storage. And so what we're going to do, we're going to look at all of the mechanisms by which energy is coming in. Looking back here, where is energy coming in? Well, it's going to be coming from all of these surfaces where we have flow coming in, or heat flux coming in, I should say. And then the last one is down there. So that's energy in, energy out. That is going to be their energy is leaving, their energy is leaving, and their energy is leaving. And then we have the storage and the generation terms on the inside of the object. So let's expand this by subbing in the values. Okay, so we get this equation. I'm going to call this equation number 1, and we will come back to this equation shortly. But that is going to be the basis for deriving the heat diffusion equation. Before we move on, though, what I want to do, we're going to use Taylor series expansion in order to work with this equation and to simplify some of the terms. So let's do a little bit of a math aside. I'm sure all of you have taken numerical methods courses or math courses, and you've probably seen Taylor series expansions. They're used quite often whenever we're dealing with equations like this. So let me just write out a little bit of a math aside. Okay, so in the Taylor series expansion, what we have, it's written in terms of some arbitrary function. And we're saying that we're evaluating this function at some point, a small distance away from where we know the functional values. So we know the function at location x, but what we want to do is we want to try to find it at x plus dx. So here we know the function, and here we don't know the function. So that's essentially what a Taylor series expansion is doing. And this is in terms of one dimension expansion, so in one direction. And then what we're saying is that we take the function plus the slope. So the slope of this function, multiplying it by dx, which is the distance between these 2 points. So if we know the slope of the function, and so let's say that is the change, so that is df by dx, and if we multiply it by this distance here, delta x, that enables us then to determine the value of the function at the next point. So that's just a linear extrapolation essentially. And then higher up here, what we have here, we call these higher order terms. And we're going to neglect those in the analysis that we're doing here. But if you wanted to do a more precise analysis, you would carry those. So looking at the Taylor series expansion, so if we have f being a function of x, y, z, which in this case we do because we're dealing with a three-dimensional system, but in that case what you would do is you would just expand about one direction at a time. But then your slope is going to be the partial derivative because you're just interested in the slope in that one direction. And then we would have the higher order terms up there. So what we're going to do, we're going to take this and we're going to return back to our heat flux, and we'll consider the heat flux in the x direction to begin with. So we're going to look at qx plus dx. We're going to hold y and z constant, and we're going to neglect the higher order terms. And so with that, we get this equation, and then I can do the same for the y and the z direction. And I'm going to call these equation 2. So we have equation 1, which was the energy balance. We have equation 2, which is basically using Taylor series expansion. And we can take these, we can take equation 1 and we can take equation 2. And the other thing we're going to do, we're going to recall our Fourier's law in 3 dimensions. So in the earlier segment, we said that we could write the heat flux vector in terms of the gradient of the temperature. So we're going to sub that into equations 1 and 2. So let's work through that. So first of all, looking at the qx minus qx plus dx, which appears in equation 1. And I'm going to use our Taylor series expansion for that. So we have qx, and then writing out how we evaluated using the Taylor series expansion. And we have plus partial by partial x, and in our Taylor series expansion we had qx there, so the heat flux in the x direction. What I'm going to do, I'm going to make a substitution here from Fourier's law for that term. So let's plug that in. And we get that term. Now what I can do, I'm going to rearrange this a little. First of all, what we notice is qx and qx is going to cancel out. What I'm also going to do, I'm going to pull the area out. And the area, in terms of the x direction, is going to be the dimensions, the 2 other dimensions. So the area, as far as x direction is concerned, is going to be dy dz. So there is the area. The minus sign disappears because it's a minus minus, and then